Alright, we're going to talk about absolute value, and I'm just going to begin with this interpretation of absolute value. It's the distance of a number from 0 on a number line. So if I take the number 3, let's say, and I want to know its absolute value, which is represented by the two bars, this means that the number 3 is how far from 0? Well, it's 3 units. And the distance is always positive, so an absolute value always comes out to be a positive value, unless it's 0. So I think the number 0 is how far from 0? Well, it's 0 units. If I'm dealing with a negative number, absolute value would mean how far is negative 3 from 0 on the number line. And again, because distance is positive, that would be 3. So absolute value is essentially the positive of the number that I'm considering, unless it's 0, in which case it's 0. Alright, so just to make this concept a little bit more precise, this is a geometric way to interpret absolute value. Our actual definition goes like this. The absolute value of a number x is the number x itself if the number x itself is positive, or 0. So if x was positive like it is here, 3, then the absolute value is that same number. Or if it's 0, it is 0. But if our x is a negative number, like it is here, then our absolute value is the opposite of this negative number, because that will make it positive. So if x is negative, its absolute value is negative x. And this is what we call our piecewise definition of absolute value. Absolute value is x if x is positive. It's the opposite of x if x is negative. So now let's jump into graphing functions involving absolute value. And we're going to do a few things with these. So the first one is a simple y equals absolute value x. And as I do when I'm confronted with something new, I'm just going to build a table of values for this and consider different values of x. So if x was 0, the absolute value of 0 is 0. If I put in any positive number, that same number will come out. And if I put in any negative value for x, the positive of that value, the negative of that negative value, which will make it positive, comes out. And so if I plot these points, you can see I'm getting a line going up on the right and another line going up on the left. And so my graph looks like selected pieces of the two lines. Okay, my domain, what values of x was I able to absolute value? Any value of x. And range is what comes out. What comes out is positive values or 0. So y is greater than or equal to 0, where y is a real number. Alright, now we're also asked here to write this function in piecewise form. Well, this is what we just talked about a few minutes ago. Y is the absolute value of x is x if x is greater than or equal to 0, or negative x if x is less than or equal to 0. Okay? This is what I call my piecewise function. So what I'm going to do now is give you another interpretation, another way to think of the graph we just built above. I could think of this as y equals x. Now you know what a y equals x graph is. It's a graph that looks like that, except that we only want this graph to happen from x being 0 and onwards. So I'm going to take away everything on the left. Okay, I want just this piece of the graph. Okay, make sure my points are accurate here. 1, 1, 2, 2, 3, 3. Okay, the other piece of the graph is y equals negative x, which we know on its own looks like all along here. But again, we only want x less than 0, so we don't want the part on the right. So I'm going to take that away. And notice what I have. I have the same function, obviously, but I've interpreted it in terms of the pieces of two lines. And that's what an absolute value graph is. It's pieces of different functions. In this case, the piece of two lines. All right, now I'm going to look at a third interpretation of y equals absolute x. And I'm going to look at it, first of all, in terms of y equals x without the absolute value. And we know that if we took the values of x that we had above, the x and the y are the same. And so if I graph those points, I get this line. Now what I'm going to do is I want to consider what happens to the blue graph when I apply the absolute value. Well, I'm still able to put the same values of x in, but what's going to come out is the positive of the y values that came out before the absolute value was there. So all of these y values are going to become positive. And if you ask yourself, what changes on the new graph? Well, any point with a negative y value, such as this point, goes above, reflects above the x-axis, reflects above, reflects above. So this suggests a third way to graph absolute value functions. Instead of doing a full table of values or considering a piecewise function, we can graph the function without the absolute value, and then when we apply the absolute value, that makes all our y values positive. Alright, so let's apply this idea to this function, y equals 2x minus 4. Alright, so I could graph y equals 2x minus 4 without the absolute value sign. And let's just do our table. Let's show our table. We know actually there's y-intercept of negative 4 and a slope of 2. So y equals 2x minus 4 looks something like that. If you want to specifically just look at the point so you can better understand what's happening, these would be the values of x and y, some selected ones. Alright, so now when we go and absolute value this, our output values for y, our new y's, are going to become the positive of the ones from before. So 2, 0, those stay the same, but these all become positive. So in terms of graphing, anything that has a positive y value doesn't change, so this stays the same. But anything with a negative y value, its new y value will be a reflection across the x-axis. And so the graph in red is our absolute value function. Okay, you can see that the domain is all reals and the range is y greater than or equal to 0. Alright, we could also interpret our absolute value function as a piecewise function. So 2x minus 4 would be equal to itself, 2x minus 4, if x was greater than or equal to, in other words, when this value is positive, and this would happen when x was greater than or equal to 2. 2 makes the inside 0, so anything greater than 2 makes the inside positive. So if this is positive, the absolute value of this positive will be the same as that inside piece, 2x minus 4. Okay, which is the blue graph above, starting at x equals 2. Which is here. So I'm just copying the graph, the blue graph from above, for values of x greater than 2. So that's the right side of my graph. And then the other piece of the absolute value is that if this is a negative value, this will be the negative of that inside thing. if x is less than 2. And you could simplify this to negative 2x plus 4, which is a graph with a y-intercept of 4 and a slope of negative 2. And this is bringing in the left piece of the absolute value function. Okay, so there's two interpretations to graphing it. Graphing the original function and then making all the y values positive, which flips anything that's below the x-axis to be above, or looking at the graph in piecewise form and graphing each piece for the domain to which it applies. Let's look at one more example. This one's a little bit more complicated because we're doing the absolute value of a quadratic function. So probably the easiest of the two approaches is to look at the original function without the absolute value and graph it. Alright, so we've studied parabolas before. We know this is a parabola opening up. It has a y-intercept of negative 2, so let's put that there. This looks like it factors pretty nicely, so let's do that. And I'm factoring it because that'll give me the x-intercepts. So this graph has x-intercepts of 2 and negative 1. And the vertex would be located halfway in between negative 1 and 2, which would be at a half. So f of a half, y of a half, would be a half squared minus a half minus 2, would be 1/4 minus 2/4 minus 8/4. That would be negative 9/4. Negative 2 and 1/4. Might be nice just to have another couple points of accuracy. If x was 3, 3 squared 9, minus 3 would be 6, minus 2 would be 4. So 3 comma 4 would be a point on the graph. And when y is negative 2, 4. Guess that's not too surprising because of the symmetry, so my graph looks something like that. Alright, so then if I want to graph the absolute value, I know that anything that's above the x-axis that has a positive y value stays the same. So these parts of the graph stay the same. And the part of the graph that has negative y values will reflect across the x-axis to be above the x-axis. So this y value of negative 2 will become 2. This y value of negative 2.25 will become positive 2.25. And so it's going to look something like that. Okay, my domain, all reals. My range, 0 or greater. Alright, if I want to think of this function as a piecewise function, it's equal to itself when the original graph is positive. Well, the original graph is positive when the black graph is above the x-axis, and that is when x is greater than or equal to 2 or less than or equal to negative 1. And this absolute value is equal to the opposite of this thing on the inside. In other words, a reflection of the black across the x-axis to become the red if x is anything else. In other words, x is between negative 1 and 2. And so I have my absolute value function in piecewise form.